Hey, in this video we'll be talking about the Bresenham line drawing algorithm, and specifically we'll be talking about it in the context of developing games. We'll also discuss some applications it could have and how it's much more useful than just drawing lines. So, Bresenham's line drawing algorithm is an algorithm. That is, it's a set of steps like a recipe, and it produces rasterized lines. Rasterization, it's the process of splitting something up into even chunks, usually on a square grid. So, such as taking a perfect mathematical idea of a line and representing it on a discrete array of pixels. Bresenham's line algorithm can be used to draw nice lines in computer graphics, but it can also do a whole lot more. Have you ever played a game where you go faster diagonally than you do horizontally? You press the right arrow, right? And you get some horizontal movement value, like 1, and you press the up arrow to get some vertical movement value of 1. So if the code naively converts these to movement, then when you press both of them, right and up, you get horizontal equals 1 and vertical equals 1 at the same time. If you take those cases as separate vectors and add them together, you end up with this diagonal line. And so if we separate these, draw these or write these as vectors, here's our horizontal vector, here's our vertical vector. Let's say our vertical is in the y dimension. And then our diagonal one, with those added together, component-wise addition there, we end up with this vector. And this one is bigger than the others. Let's check the magnitudes. The magnitude of the horizontal one is 1, of course. Magnitude of the vertical one is 1. Yep. The magnitude of this one is going to be something like the square root of 2. That's about 1.4, let's say. 1.4, that is significantly greater than just moving in one of those directions. This is a fact of life for games that use square grids and allow diagonal movement, but it also happens in some real-time action games too. When this happens, it's just simply more efficient to move diagonally around obstacles. As a side note, you can fix this by normalizing these input vectors, this final input vector, before you apply it to the movement. That'll fix it all up, and in a real-time game, freeform movement, you wouldn't move faster diagonally. So a lot of games do that. Alright, so how does this apply to rasterizing lines, to drawing these lines? Well, in Bresenham's algorithm, we recognize that when drawing a line from one pixel to another, we always advance along one of these axes exactly 1 pixel at a time. So I have here just a couple of coordinate axes, x and y. We'll do this in 2 dimensions. So one of these axes, we're always going to be advancing as we draw the line 1 pixel at a time. We'll call that the fast axis. The other axis, if we're drawing a line, the other axis will move up every once in a while. It's going to increase either by 0 or by 1 each time. So we'll call that the slow axis. So in this case, x is going to be our fast axis, y is going to be our slow axis when we draw that line. With that understood, we can recognize that there is a lot of symmetry in this problem. If we drew a bunch of rasterized lines, we would see that there are 8 octants, where the pattern the line creates is identical, just with the axes switched around or negative or whatever. So here are those 8 octants. Here's a line that looks very similar to this line, except their x and y are switched. This line looks very similar to that last one, except that it's negated in the x direction. This one has its x and y switched. This one's negated relative to that one. Switch the x and y, negate something, switch the x and y again, negate it to get back where we started. So 8 different sections, different lines here in different octants. So let's focus on this first octant. This one where the x direction is the fast axis and the y is the slow axis. So this is the mathematical octant between 0 degrees and 45 degrees. So we can focus our solution on just one of these octants, and then knowing how the octants differ, we can come up with a general solution. In this octant, we know that x is the fast axis. We can start at our first point and then add 1 to our position. Here's our first point. We add 1 to our x position. But then we have to decide, is that the right place to go? Do I need to add 1 to my y, or do I want to add 0 to my y, staying the same y coordinate? To make a continuous line in this octant, we'll only ever add 0 or 1 to our y position. We just have to figure out which one to use, 0 or 1. To do that, let's compare our ideal math line to these options. So let's say this is my starting pixel. I'm going to move over 1 pixel. So here's where I start, the center of that pixel. And here I might go to this pixel, or I might go up to this pixel. And let's say we have a line drawn like so. We might have a wider grid. Let me just show some of that here. Okay, so which one of these options is the right one? You could probably guess from my drawing here that it should be the bottom one. I should not add 1 to my y coordinate. But we need to actually calculate this and tell the computer how to make this decision instead of us visualizing a nice straight line and seeing where it overlaps the pixels. So what we want to do is compare to our ideal line. We know what y coordinate the perfect math line would have. So we can compare that to our guess, this y plus 0 coordinate. If the y plus 0 coordinate is too far away from our ideal line, then we should use our y plus 1 instead. When we compare our ideal line to our rasterized one, it's useful to describe that difference between the two as an amount of error. That's how far off we are from the true value. We could calculate the true value using our line equation and plugging in the slope and the y value. Then we could compare it to the y plus 0 point right here, and we could see if we're too far off. Since we're talking about pixel centers, which are 1 unit apart, we want to have an error threshold of 0.5. If we are farther than 0.5 from this ideal line, then we need to add 1 to our y value. We know that we've gone too far. All right, let's back up a second and calculate that slope. We're going to need it. To draw a line between 2 points, we have to be given the coordinates for those 2 points. Lines are linear, so the slope between them is constant, of course. So we can use some understanding of slope. Let's call this x1, y1, and this one is x2, y2. We know that the slope can be defined as the rise over the run. So the rise is the vertical change, and the run is the horizontal change. If I want to find the difference between these 2 points, I subtract their coordinates. So our rise is a delta y, change in the y coordinate. Our run is a delta x, change in our x coordinate. And then our slope is going to be delta y over delta x, or the difference in the y values divided by the difference in the x values. Okay, let's get back to that threshold. Again, we could calculate the expected value of our y coordinate from the original line equation, y equals mx plus b, and we could subtract that from our value. We are guessing that we're going to end up at y plus 0. That would give us a value for the error, just taking the difference between those 2 points, telling us how far off we are. And that's exactly what we would do for more complicated shapes than a line. However, lines are simple. Every time we take a step in the x direction, the true y value always increases by the slope. Exactly the slope value. So if we keep track of this error amount, adding the slope each time we take a step, then we can easily see if it's greater than 0.5. Whenever we've added enough slope, taking one step at a time, to get over 0.5, we know we need to go up 1 pixel. So we can look at this error sum idea as a kind of optimization. So if this accumulated error is greater than 0.5, we use y plus 1 as our next y value, and then we subtract 1 from the accumulated error to reflect that we've moved 1 in that direction. If the accumulated error is less than 0.5, then we keep our y value as it is for now. We proceed until we get to our destination's x coordinate, so we can keep taking these steps and figuring out if our y value needs to increase or not. And we will keep doing this until we get to our destination x coordinate, wherever our line wanted to end. And that's a loop from x1 to x2. Alright, how about a demonstration? Let's go through our logic. I'm going to draw a line between 2 points. So let me make a kind of coordinate system. And this coordinate system, I'm going to make it pixel centered. So 0, 0 is going to start off right in the center of our math coordinates there. And I'm going to draw a wider grid of pixels that are going to have their centers fall on the math coordinates that they're represented by. Alright, so let's draw a line between the points 1, 2 and 6, 4. 1, 2, 6, 4, following this algorithm. So where are those points? 1, 2 starts here, and 6, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. All right, there we are. Between these 2 points. All right. My slope is the difference in the y coordinates, so 4 minus 2, divided by the difference in the x coordinates, 6 minus 1, that is 2 over 5, and that is 2/5, so 0.4. So draw a point where I start, so that's our first pixel. We know we're starting there. I can draw that in. And then go in the fast direction. With this slope, I'm going fast in the x direction. Adding 1 to my x brings me right here. So adding the slope into my cumulative error, let me get my error. Let's start off at 0. Once we take one step in the x direction, there's some error, some difference between my current point and the line. That amount is the slope, like we said before. So my error is going to be 0.4 at this point. That's not greater than 0.5. So I'm going to stay at this y value. That means this is the correct pixel to draw. Okay, now I go to the next one, next x value. I add my error, add my slope into my error again. So this is 0.8 now. And this is now over my threshold of 0.5. So I know I need to add 1 to my y coordinate, and that is my final pixel. All right, keep going. Move on to the next x value. Oh, I forgot. I need to subtract 1 from my error, my accumulated error here. So I ended up with negative 0.2, which means that the coordinate I actually landed on was above my line. I overshot my ideal line, but it's still closer than the other option, staying with my old y value. So this is better than it was, closer to 0 error. Alright, so let's go to the next pixel. Move over x. That's going to add 0.4 into my error. So now I've got a positive 0.2, and that's still below 0.5. So this is the correct pixel. Alright, move one more, add a bit, add my slope into my error, 0.6, alright, go up 1 then, and then subtract 1 from my error, negative 0.4. We'll step over 1 more in the x direction, add to my error, and well, this one works out nicely. It looks like I landed right on that spot. No error, but I just need to check that it's less than 0.5. It is, so I stay at that x value. I've also reached my target x coordinate. So 6 was what I was going until I got there, and now I can stop. Okay. So that's kind of crazy. We can now draw a line, but only in one octant. So let's apply that symmetry. One symmetry is for lines with a negative slope. So the differences between a line with a negative slope and a positive slope here. So the slope that we're adding into our error actually needs to be the absolute value. That is because the threshold we're using is 0.5. It's always going to be positive. So and we're only ever increasing our slope error in one direction. So it doesn't really matter. This just makes it easier to compare to 0.5. So let's make it always positive. And then our y value instead of taking one step in the x and increasing by our y value by 1, we decrease our y value by 1. So let's parameterize that change. Let's say we have a y increment. That's 1 normally. But if we're in this quadrant, the lower quadrant or octant here, so if our delta y is negative, then this increment should be negative. Y increment equals negative 1. All right, and then we can go on, and our whenever we change our coordinate, it's going to be y plus that increment instead of just y plus 1. That way it can be negative. All right, the next symmetry. So steep slopes are just like low slopes. Here's a low slope, here's a steep slope, but the x and y coordinates are swapped. So we can make a version of our algorithm so far that's pretty much just a copy and paste of whatever code you might write for the for those other two octants. And this code marches along the y-axis as the fast axis instead of x. And it checks the inverse of the slope. So our inverse slope would be just flipped. Make y our fast axis and x our slow axis. The increment and tests need to apply to the x value instead of the y value, and that slope is flipped. All right, and the last symmetry to deal with is for the octant where the slope is the same. So here's my coordinate system, here's a slope, and there's another line that would have the same slope on the other side. We could reuse the same steps as long as we start from the correct side of this line. We were able to follow some steps to go up this slope, so if we set up our points so that we're still just going up this slope, we follow the same exact steps. So we can check to see if the second point we're given is actually to the left of the first point. And if they are, then swap them. So if we're given a line they want us to draw like this, we can detect that. We can say if delta x less than 0, then we swap them. You could also check to see, this is the same as putting like if x2 is less than x1. Then we can redirect this and use the same exact code, just swapping these so that this is x1, y1, and this is x2, y2. All right? So we should get the same resulting line. We'll want to compare the y values instead of the x values if we are talking about steep slopes. So we would have code to do a steep slope, and to do the equivalent steep slope the other direction, we want to check the y values there and make sure that they're in the right order, and if they're not, swap them and just use our old code. All right, great. So that was a fair amount of work, but conceptually, that's all we need in order to render rasterized lines using the Bresenham line drawing algorithm. What else can you use rasterized lines for? How about placing units in a strategy game? You might want several rows of soldiers lined up between 2 points. Instead of drawing a pixel at each point of a rasterized line, imagine that you're instantiating a soldier game object at each pixel. Want to check the line of sight for a grid-based game? Well, use this algorithm. See if a line hits any grid cell that has something blocking in it. There are tons of applications, and I hope you'll explore them. Check out this algorithm, implement it, add it to a game you're working on, and have fun. And I'll see you later.